Hello, this is Mr. Hammond-Beyer, and this is lecture 12, fossil fuels. So we'll talk about energy and energy stored and converted. So let's start with some calculations. 1 gallon of gasoline equals 1.3 times 10 to the 8th joules. Joules is kind of a measure of energy. 1 calorie equals 4.814 joules. So after your recent experiments with cashews, you understand the calorie. So 1 calorie is equal to, this is calorie, not kilocalorie, equals 4.8 joules. Okay? So how many calories in 1 gallon of gasoline? So you have 1 gallon equals that and that. How would you set that up? Stop the video, take a second, see if you can do the calculations. When you come back, here's how I would have set it up. 1.3 times 10 to the 8th joules equals 1 gallon of gas. So whenever you have an equality horizontally, you can change it into an equality vertically in dimensional analysis. And you know that 1 calorie equals 4.814 joules. Multiply everything across the top and everything across the bottom, and you end up with, and then divide the top by the bottom, and you get 2.7 times 10 to the 7th calories. Or 2.7 times 10 to the 4th kilocalories per gallon of gasoline, since kilocalories is a more common application. Now, while we're on this math theme, let's take a couple more problems. All right, so 1 barrel of oil equals, if you've ever seen those barrels, big jugs or barrels, equals 42 gallons of oil. Okay? In that 42-gallon barrel, there are about 19 gallons of gasoline, besides all the other stuff that's in the oil, in crude oil, or 1 barrel of oil equals 19 gallons of gas. Now, 1 gallon of gasoline equals 10 pounds of coal, or 150 cubic feet of natural gas. So if we have 1 gallon of gasoline right here, 6 pounds, that's equal to 10 pounds of coal, or 150 cubic feet of natural gas, just to give you some equivalence. Now what I'm going to ask you to do is a mileage log. So I know we're not driving a lot right now, but in the future, keep track of how much you drive and how many miles to get per gallon are you getting. So in other words, every time you fill up your car, set your trip odometer at 0, drive around. When you go fill up again, record the number of miles you have on your odometer, reset it to 0, and divide that by how many gallons it took of gasoline to fill your tank. With my Toyota Tacoma 2005 pickup truck, I get between 18 and 20 miles per gallon. Not really very good. Okay? Based upon how many miles you drive per week or per month, how many barrels of oil do you need per month or per year? In other words, how much oil are you consuming? And unfortunately, I consume way too much because I drive from Aiken to Augusta and back every day. It's about 50 miles or so, and I have to fill up every week, which is 18 gallons. Okay. All right, so let's take a practice problem to see how this works. So assume you drive to Atlanta, which is 187 miles one way, in your Nissan Sentra, which gets about 31 miles per gallon. Gas costs $2.15 per gallon. 2 questions. Number 1, how much does your round trip cost? And number 2, how many barrels of oil did you use? So again, stop the video, do the math, see if you can figure this out. Okay, so the solution starts with, well, you drove a total of 356 miles there and back. All right, so if you drove 356 miles and 1 gallon equals 31 miles, so that way you can get rid of miles, and it costs you $2.15 per gallon, so now you can miles will cancel out, gallons will cancel out, and you're left with costs. So 365 times 1 times 2.15 divided by 31, and you end up with it costing you $24.69 just for gasoline. Now, how many barrels of oil did you use? Well, you drove 356 miles, and you know that 1 gallon gasoline gets you 31 miles. So you used a total of 11.48 gallons divided by 19 gallons per barrel, and you get 0.6 barrels of oil to drive to Atlanta and back. And Saudi Arabia produces how many million barrels of oil a day? Okay, kilowatts and kilowatt hours. Now, we have electricity to run the board and to turn on the lights, and a kilowatt is equal to 1.34 horsepower. And a watt is defined as 1 joule per second. So go back to the beginning, we talked about joules. All right, 1 joule per second. So you're making or using enough energy every second to make it equal to a joule. All right, so the rate, that's really where we really want to end up, is right here with kilowatt hours. And kilowatt hours is the unit of energy equal to 1,000 watts times the number of hours you use. In other words, if you use 1 hour, 1,000 watts in 1 hour, you'd have 1 kilowatt. And that equals 3.6 megajoules. Okay, so kilowatt is the product, kilowatt hours is the product of the power you use times the amount of time you use it for. So if I have the lights on for 3 hours, and they're using 100 kilowatts, so that's 100 times 3, or 300 kilowatt hours. Okay, now, how do we get from crude oil to gasoline? Well, in comes the crude oil. It's heated up gently, and it uses what's called fractional distillation, where it separates based upon the atomic mass of the parts of the oil. So the stuff that's heavy, the sludge and the residue, stays down at the bottom. Fuel oil is also pretty heavy. All right, the stuff that comes off very quickly or easily is gasoline or petrol, and that's what's used in cars. That comes off at about 70 degrees, has a boiling point of about 70 degrees. Naphthalene, which is a type of kerosene used to make a bunch of chemicals, 120 degrees. Kerosene is 180 degrees. Diesel fuel comes off at 260 degrees. So as this first starts to heat up, the stuff that gets hot fast comes off very, very quickly. And they heat it very gently. They don't want to burn and blow everything up. So they heat it very gently, and it separates out. The stuff that's left is asphalt and tar, stuff that they put on roads. Okay, whoops. All right, so what we really want to know, or want to look at a little more closely, is gasoline, which, if you go to a gas pump, you'll see an octane rating. And what is octane? Well, octane is oct, 8 carbons and hydrogens. So you've got CH18. In your automobile, you are mixing that CH18 with oxygen to form a combustion, which then forces your cylinder down, which forces your camshaft to turn, which then causes your transmission to push your wheels. The more cylinders you have, the more of this you use, the more explosion you have, therefore the more power you have, theoretically. Okay, so the molecular mass of octane is 114, carbon dioxide is 44, that's atomic mass units, oxygen is 32, and water is 18. So let's look at this a little closer. So to combust 1 kilogram of gasoline, think about it, that's 2.2 pounds of gasoline. A gallon of gasoline equals about 6 pounds. So a third, a little bit less than a third of a gallon of gasoline requires 3.5 kilograms or 8 pounds of oxygen. And it gives us 3.09 kilograms of carbon dioxide and 1.42 kilograms of water and a lot of heat. So think about this. For every third of a gallon of gasoline you burn, you're putting out 7 pounds of carbon dioxide into the atmosphere for a third of a gallon. Okay, and I know if I'm burning 18 gallons a week driving back and forth, 52, 54, dioxide per week. I'm sorry, kilograms of carbon dioxide per week. So I'm driving back and forth to Aiken, from Aiken to Augusta, I'm putting a lot of carbon dioxide up into the atmosphere, which, considering that there are green plants that are absorbing some of that carbon dioxide, it shouldn't be an issue. But obviously we've tipped the balance. Okay? So energy conversions, what are we really doing with this? So we're taking chemical energy in the form of octane or hydrocarbons, and we're combusting them to give us heat energy, which is what we really want, and then we're using that heat energy to drive a machine and convert it from heat energy into mechanical energy. And from mechanical energy, then we are using a generator to turn that into electricity. So the bottom line is, how do we turn on the lights? We're going to use these types of things, and let me explain this process. So in this case, here's a schematic of this is a nuclear reactor, but it could be a coal or natural gas-fired power plant. But over here, you have the reaction occurring, and the reaction is heating up the water, and the water is then running through a closed system, because in nuclear, you don't want any of the nuclear material getting out, so it stays in a closed system, but it heats up water over here. So at Plant Vogtle, a nuclear reactor, they are heating up a whole bunch of water. That water is then converting from liquid form into steam. The steam is now under pressure because it's expanding, and it runs a turbine. The turbine spins, which then runs a generator. And the generator is an magnetic coil, so it's a whole bunch of wraps of copper around magnets. Those then generate electricity. Okay? So the steam coming through the turbine then has to cool, and that's cooled off by water coming in Plant Vogtle from the Savannah River. It cools off and then goes through the cycle again. Or if you go up to Duke Energy in Pickens County, it's the same basic process. We can change the heat source very easily. Make it natural gas, where now we don't have to heat up water to heat up. We don't have to heat up water to heat up the water. In this case, we're going to just have boilers underneath the water, and that's going to heat up and run this system. So we take one little step out of there. Same thing with coal. But the process is the same. The water turns into steam, is heated up. The steam is under pressure, drives a turbine, which then spins a generator, which then generates electricity. The farther the generator is from the source it's used, the more electricity is lost, because electricity is not 100% efficient as it runs down the wires. So the closer we can have these to large urban areas, the less electricity is lost in the wires. But then, if this is close to a urban area, then you have other problems or considerations, which we'll talk about in a minute. Okay, so if we look at selected prices of crude oil, if we're going to run either our cars or natural gas or power plants, the crude oil back in April of 2018 was selling at $62 a barrel. Okay, in 2015 it was $41 a barrel. Well, there was just a big row between Saudi Arabia and Russia, and with the COVID crash, the demand for oil has gone down. Yesterday the cost was it was selling at $20.61 a barrel. So half of what it was in 2015 and a third of what it was a year ago. If you look at that was as crude oil, as gasoline, on the wholesale market it's selling at 63 cents a gallon, whereas it was $1.81 a year ago and $1.43 in 2015. So right now oil prices are really, really low, which is going to tend for people to be want to say it's okay, oil is cheap right now, I can use lots of this resource. I'm not sure how long that will last. Okay, so where does our energy right here in the CSRA come from? If you go to this website, there'll be a map there, and it'll have little icons on the map that will show you most of the electricity producing sources for our area in the Augusta-Aiken area. Plant Vogtle produces about 3,202 megawatt hours. Hydroelectricity, Augusta and Aiken are fortunate that they're on the fall line. So there is Clarks Hill, and then in Augusta there are 3 other hydroelectric facilities, and they produce about 378 megawatt hours. There's a natural gas plant down in Beach Island which produces about 150 megawatt hours. It's the one that's very variable, so when demand is low it produces less. When demand is high in the summertime and everybody's got their air conditioner on, it goes up to it can double that number easily. All right, and then there are solar fields in Aiken and Augusta, and they produce about 100 megawatt hours, sorry. You can see this is 3,000, everything else is down in the hundreds. So by far, the biggest electricity producer in this area is Plant Vogtle. But now that doesn't all come to Augusta, that goes out on to the entire system. Okay, so what are non-renewable fuel sources for perspectives from this class? It's coal, petroleum, natural gas, and nuclear, just because we can't make them in a timely fashion. And how much energy do each of those get? Well, if you look at thermal energy, the calorie content, and that's kilowatt hours per kilogram. So if we had a kilogram of brown coal or lignite, we'd get about 2.8 kilowatt hours out of that. Whereas natural gas from the North Sea is about 10.8, and LPG, that's if you go buy one of those things to run your grill, that gets you about 13.8. We're getting a little bit better. Kerosene from gets about 13.0. Gasoline is 13.0, and diesel is a little bit less at 12.9. Biodiesel, even not as good as that at 10.8, so that's a mixture of, we'll talk about biodiesel later. Uranium, way off the chart. 22.5 million kilowatt hours per kilogram. So if we have uranium, it's not even close, not even in the same ballpark. Which, if you're an energy specialist, you would say, well, why don't you go with this because you get so much more bang for your buck. And let's look at world electricity generation. From 1971, here we were at about 5.7, and this is in terawatt hours. And by 2004, we were up to about 17,000. And notice where most of it was coal. There was a pretty big strip of oil in here, and gas, and nuclear, and then hydro, and all the others have been relatively thin. If we look at world energy consumption worldwide, most of the world energy consumption from 1985 to 2015 is in fact fossil fuel based. Then there's a band in here of nuclear, a band of hydro, and then very thin bands of geobiomass, wind, and solar that have emerged and taken a little more prominence in the last 10 or 15 years. So between 1971 and 2004, note that electrical energy generation more than tripled from 5,200 to 17,400 terawatt hours in 23 years. So we have tripled our energy generation. Why? More and more of humanity wants to have electricity when they go home. And what happened from 2010 to 2015? Notice there is a little dip right in here. Why? Economic recession, okay? And which sector seems to be growing the fastest? So if you look at these, who's growing the fastest? Well, all right, we can have a bias, but here's how this is in 2014, generation by source. So coal was at about 39%, natural gas was about 39%, nuclear was about 19.5%, hydroelectric was about 6%, wind was at about 4%, solar, geothermal, and all the others, yeah, they ended up to pittance. Okay? Okay, this was in 2014. Natural gas has taken over a little bit of the coal since that time. Nuclear hasn't expanded much. Hydroelectric hasn't expanded much. But wind and solar have expanded some. Geothermal hasn't really caught on very much. Okay? So if we look at, basically renewable energy is about 10% of the US energy consumption. And where is that? Most of it's hydroelectric, 25%. Some of it is wood for people burning wood-burning stoves. Biofuels is catching on and getting more and more popular, 22%. But geothermal and solar and wind still are not picking up nearly enough. Okay? In 2016, again, of that 10%, the biggest percentage of that was hydroelectric. Wind, biothermal, and solar. Solar's still down at near 6%. Now, who are the biggest world consumers of energy? In 2015, China had 3,101 million tons of energy consumed. 3,000 million tons of energy. The United States was at almost 2,200. Everybody else below that was less than 1,000. So there are these two giants, and then everybody else is kind of, their economies are not using nearly as much energy and weren't in 2015 as China and the United States are. We look at it in 2019, China has gone up to 3164, so not much of an increase. The United States has gone up to 2258. Again, India, Russia, and Japan are in the same position. Certainly India has bumped up a little bit, as has Russia and Japan. Germany and Canada are down at 301 million tons of energy. Okay? Okay, so if we pick these apart, nuclear, I'm going to put nuclear on the hot seat for a little bit because nuclear has started to grow, but there are some issues. Okay? In April of 2017, there were 30 countries with 449 nuclear reactors, and there were 60 new plants under construction in 15 countries. And that's about 11% worldwide of the production in 2014 versus 20% in the United States. Okay, how does nuclear work? So we send a neutron into a U-235 atom, and it smashes and splits it apart. When it splits it apart, there is all of this energy that is released, and the neutrons, and then that heat energy can be used, as we saw before, to heat up water, which then heats up other water, which then runs steam and runs a generator. Okay, and that will, over time, decay, but it can be replicated. In other words, it starts a chain reaction, which then runs on for a long time. How much energy is that? So this one little pellet is equal to about the amount of energy of about a ton of coal, or 17,000 cubic feet of natural gas. In that one little pellet. Now, that's not a pellet of uranium. I think I couldn't be touching it, but that's symbolic of a pellet of uranium. What happens with those pellets of uranium, they go into a fuel rod, and the fuel rods then go into the reactor core, or the fuel assembly, which then goes into the central rods right here, and they can be moved up and down, and that regulates how much steam is produced, or how hot this temperature is, and then how much steam is produced, and then how much electricity is generated. Okay. Of those 400 and some odd reactors, France had 78% of its nuclear, of all of its energy was generated by nuclear facilities. Belgium came in next. Belgium and Slovakia at about 54%. Notice the United States is way down here at about 20%. So about 20% of our total energy was from nuclear sources, compared to some countries that had invested quite highly in nuclear. Notice that Japan was only at 18%. There are here's why these things are changing. Because of the tsunami, take a few minutes and watch those videos, but at Fukushima, which was a nuclear reactor in Japan, here's their cool water exchange. This was right on the coast, and they had 6 basic units set up until there was a shift, an earthquake off the coast of Japan, which then sent a tidal wave to Japan. And here's the wave coming in, and it just destroyed many parts of the eastern side of Japan. And here are the reactors burning after the tidal wave came through. Here's some of the destruction, and here's the tidal wave coming over. This was the highest retaining wall in the world, and the tsunami came right over the top of it. And you can see it was taking vehicles with it, all kinds of stuff. And here is the nuclear plant flooded. When it came over all of those retaining walls and flooded the nuclear reactor, what happened was the water came in and got close to the pressure vessel, which then released radioactive steam into the atmosphere and out into the ocean. So here is the explosion of some of the Unit 1 exploding after the tsunami. Okay, so what happened after that? In 2019, China and Russia have the largest number of planned nuclear reactors, and they are rethinking that very, very closely. France, which had about 70% of its total electricity generation derived from nuclear sources in 2018, they have certainly changed their policy and are going to rely less on nuclear after this kind of event, although tsunamis are not likely in France, but nonetheless any kind of earthquake could have caused some of these types of problems. Okay, so as we look to the future, where are we going to get our energy and our electricity? Well, liquid gas or natural gas in 2020, so this is the percent of, for each source, no, this is the trillion kilowatt hours, okay? So here are trillion kilowatt hours in 2020, we're getting that many, 0.63 trillion kilowatt hours from liquid gas. Natural gas, 5.9, coal, 8.5, nuclear, 2.7, renewables, and hydro are at 8.9, for a total of 26 trillion kilowatt hours. By 2030, that number's gone up to 31, but notice some of the shifts away from liquid gas, increase in natural gas, a slight increase in coal, nuclear is a slight increase, but renewables have gone up significantly. Then by 2050, liquid is way, way down, natural gas is significantly higher, coal's a little bit higher, nuclear is a little bit higher, and renewables are much higher, but we need, or are projected to use, 44.18 trillion kilowatt hours of electricity. Okay, so your task is to graph the percentage. So of this 26.68, so 0.63 divided by 26.68 times 100, get the percentage in 2020 and compare it to the percentages in 2050. So what's our distribution going to look like compared to these two? You can either put it in a pie chart or in a multi-line graph. That's up to you. And I believe that concludes this lecture on non-renewable energy.